好，大家早安。那我们就要开始喽。我等一下就会开始切换成英文这样。那我们的in our homework, there is some materials that have not been mentioned in the class because we are going to reach that part after a few weeks. So, but you still need like some like preliminary knowledge about these things. For example, linear independence. So we just need to look at the definition of it. So basically, to define what is a linear independent set of vectors, we need to consider a sequence of vectors. We consider a sequence of vectors. And so those vectors v1, v2, and vk is said to be linearly independent if there exists scalar, not all zero, such that the calculation a1 times v1 plus a2 times v2 plus till ak times vk equals 0, where 0 denotes the zero vector. And it's the same thing to say that the only solution to have a linear transformation on the left-hand side equals to 0, being all solutions are 0. And when solutions are all 0, we call that kind of solution as trivial solution. So this is exactly the same thing to say that a linear transformation that result in a 0 vectors on the right hand side. The only solution of that is the 0 solution, exactly the same thing. And then because that statement is lengthy, so people create a term called linearly independent to describe the relationship like this kind among these vectors. So you have to have a set of vectors given to you first, and then you're going to describe whether these vectors are linearly independent or they are linearly dependent. Okay, so they are independent if the only solution is the trivial solution. They are dependent if you are able to find non-zero solutions such that the transformation equals to 0. All right, so let's go back to the our lectures. Okay, so last time we mentioned about row operations, and you need to be have some impression about row operation. There are only 3 of row operations: replacement, interchange, and scaling. And every other type of operations like powers, multiplications, or transpose, inverse matrix are not a part of row operations. When we talk about row operations, we only mean one of the 3 things: replacement and interchange 2 rows, or scaling, multiply all entries in a row by a non-zero constant. So that's the 3 row operations. And so the next things we are going to do is called forward row reduction. And row reduction uses the uses the 3 main row 3 row operations. To do the job. So this is an example. We have a very large matrix, 4 by 5 matrix. And then the example wants us to row reduce the matrix A to an echelon form. Later, we're going to introduce what is an echelon form. Basically, it means that we are having like a zeros on the bottom left. So, okay, what is an echelon form? Eventually, we want to reach this kind of situation where there's a like a stairs, looks like a stairs, and then all the values below the stairs are zeros. Okay, so we want to like have some like operations. Basically, we're going to use operations. Okay, so this is the original A. Then we're going to like perform several steps to eventually reach a echelon form. And in the process, we can only use one of the three operations. Basically, replacement, scaling, and interchange is doable. Everything other than that is not acceptable. Like just to, you need to remember that we can only use the three things: replacement, interchange, and scaling to reach some type of matrix. And in the process, all the process are called row equivalent. Those matrices are called row equivalent. Row equivalent matrices. As long as you perform, like we stick with the only three row operations, then the resulting matrix are all row equivalent. So here you see 1, 2, 3, 4, 5 matrices. All these matrices are row equivalent. So we'll see what's the relationship between 1 and 2. How do I get matrix 2 from matrix 1? So basically, I replaced the first row. The first row is replaced in the second row. And how to replace that? I can multiply, replace, or what can I do? Oh, interchange the order of first row. If I interchange the first row and the first and the fourth row, matrix 1 becomes matrix 2. And since interchange is one of the allowable row operations, so we could say matrix 1 and matrix 2 are row equivalent. And they are row equivalent, we can use this symbol, like this symbol to say that this matrix and this matrix is row equivalent. Like a波浪, like a wave. So we now obtain matrix 2 by interchanging two matrices. And what's next? In the next step, okay, here they want to do the replacement. Basically, we see that in the matrix 3 and matrix 3, row 2 and row 3 are not the same with matrix 2. So it means that the second row and the third row are replaced with respectively by different multipliers. So different multiples. So we can like multiply the first row by -1 and add to the second row. and also multiply by plus 2, and then add to the third row. So the result is like this two row. So we can do the calculation like 1 times -1, which is -1, and then no, what should I do? The multiple should be okay. 1 times +1, 1 times +1, and then that's +1, and then add to the second row. So 1 minus 1 becomes 0. And 4 times 1, that's 4. Subtract 2, and then that gives me 2. And then 5 times 1, subtract 1, will be 4. -9, subtract, add 3. That will be -6. And then -7, add 1, that will be -6. And then in order to replace the third row, I need to multiply the first row by +2. So I have 2 minus 2 becomes 0, and then 4 times 2, 8, minus 3 becomes 5, and then 5 times 2, 10, minus 0 becomes 10. -9 times 2 becomes -18 plus 3, and then I get -15. -7 times 2 becomes -14, and then subtract 1, I get -15. So now I get the third matrix. Again, it's row equivalent, so we can write such a wave shape, 波浪状 notation to describe the relationship from the second matrix to the third matrix. So I think that you have used these notations in the past, but probably do not know the meaning of it. And it actually do means something. It means row equivalent. They are not equivalent. You cannot use the equal sign, but they are row equivalent. So they are equivalent in some special definitions. So you are able to use such a notations right here. And this notation is much better than the arrows 箭头. The wave notation is better than the arrows notation, because you know that the wave notation means that it's similar or approximately equal. And here it simply means row equivalent. The matrix are row equivalent to something something, and then you can continue to do your row operations. Okay, then next because we have not reached something called echelon form. Like we still have a chance to continually make more elements 0. So we will continue to do the forward row reduction. Okay, so how do I obtain the next? So we see that the third and the fourth rows are replaced. So this is one of the basic row operation, one of the 3 row operations called replacement. So we can do that. So they are still row equivalent. I multiply the second row by how much? Negative 5/2, and then add to the third row, and then multiply by 3/2, and then add to the fourth row, and then that will cancel many of the elements. And so it seems that the second row and the third row has a proportional relationship. So now the third row are becoming all zeros right here. So we are unhappy that there is still value below that. Here, there is a -5 that's below the 0 value. We don't want that happen because that does not satisfy what echelon is required. An echelon form, all the zeros needs to be below the non-zero values. So then I continue to make the next row operation, which is interchange. So I interchange the third row and fourth row, and eventually get my matrix 5. Okay, and okay, the matrix is in echelon form, and thus reveals that the columns 1, 2, and 4 of A are pivot columns. So this is something we do during the process called pivoting. So we select the values that we use to do the multiplication. 在过程中，我们曾经挑了一些数字，然后把那些数字作为基础去乘以某一个 multiples， 然后呢，把那个 multiples 拿来消除它其他的 rows 的某些项目，让它变为0。那拿来做那件事情的那一些 value 被叫做 pivot。So what are the pivots? Recall that in the process we did several row operations, and there is a number that we chose to multiply something in order to cancel out the values, the positive values, and then make those values 0. And those important values in the process are this one. This is the first important value, because here we continue to use this value right here to multiply +1 and then +2 and then add to the other rows. So this is called pivot. This guy is very important, the first pivot. Without this number, we are unable to cancel out the values into 0. So this is one pivot. And then the next important value is this one. We have been using here, like multiply by -5/3, 5/2, sorry, and multiply by 3/2 in order to cancel out, to make the values below it below it 0. So this is the second pivot. So here it says that it's pivot. Again, another important guy. And after we do the interchange, some values appear right here. So at this position, we also call this one pivot, because the position it's located at is important. Okay, so eventually in this echelon form, we get the value 1, value 2, and this value -5. These three things are called pivots. And corresponding to the pivots are called pivot columns. Pivot columns. So first row, second row, and the fourth row becomes pivot columns. So that's in order to make it easier to describe, we have some names for that. So here's the result or the conclusion. So eventually we reach an echelon form, and the echelon form is this one. I have 1, 4, 5, -9, -7, and then 0, 2, 4, -6, -6, and then 0, 0, 0, -4, 5, 0, 0, 0, 0. This is the echelon form. And also I have 3 pivot positions, 1, 2, and 3. And then you can also match these positions with the stair shape. 跟阶梯状的那个 echelon form 做一个比对。And then we will find out that the pivot position is the place where we have a break point. 就是在阶梯的时候，突然往下降一梯的时候，那个在角落位置 ，the corner points are the pivot position. And also after you find out the pivot position, you can identify in the meantime what are the pivot columns. Pivot columns are the columns where the pivots are located. So, okay, then here's another example, but asks us to continue to, other than just reduce it to echelon form, we can continue to reduce it to a reduced echelon form. Okay, so maybe the process of it, you can read it on your own. And in the basically it's a step by step procedure to do the forward row reduction. So after a few of the steps, and because this corner is 0, so the first step is to do the interchange row 1 and row 3, and then use 3 as the first pivot to cancel out the values below it. So now you see that here we already obtained the 0, 0 below the pivot 3. And we can continue to select the next pivot. Now we select 2 as the pivot. And this is the new pivot column. We're going to cancel out 3 and want it to be 0. So as a result, this becomes 0. And the good part is that many other elements on that row becomes 0 as well. So we can now select the next pivot being this one. And that's already an echelon form. This matrix, we have select 1, 2, 3 pivots for this matrix, and then that leads us to an echelon form. And now we have a formal definition of the echelon form. So we call a rectangular matrix. A rectangular matrix which is not a square matrix. It can be a matrix like this, or a matrix like this. So the properties of echelon form is, first, all 0 rows are above any rows of all zeros. If we have, give me a second. Okay, if we have a row being all zeros, we want to do the row interchange to make those rows of all zeros, like a row containing all 0 components to the bottom of that matrix, in order to gradually reduce to echelon form. And for the second, each leading entry of a row is in a column to the right of the leading entry of the row above it. So what is a leading entry? Leading entry is the first element in that row being non-zero. Okay, later we're going to see examples for that. And for third one, all entries in a column below a leading entry are zeros. So if we have a leading entry being non-zero, so all the components below it must be all zeros. We have 3 things. And then, okay, it's much easier to see an examples, but you still need to have some conceptual images about what an echelon form is, and then sometimes you do the row operations, but forget about the definition of echelon form. It means that you might probably have not yet stopped before you find a echelon form. Okay, so let's consider this matrix. The notations are, if it's a leading entry, we put a black box to mean the leading entry. And I just say that the leading entry is the first non-zero entry of a row. That's a leading entry of a row. So we look at the rows. If it's 0, then that's not going to be the leading entry. Star means the star entries may have any values, including zeros. But leading entry must be non-zero. So star are any values, but the leading entry is the first non-zero entry of that row. And so we see that all the zero, this is called all zero row, and all zeros row. All zero rows are below the non-zero rows. This is a non-zero row. So it satisfies the first property of the echelon form. And what about the second? Each leading entry of a row is in a column to the right of the leading entry of the row above it. Okay, so it means that 每一个 leading entry 它都一定要是在它的上一个 row 的 leading entry 的右边的 column. Okay, so we are comparing with the column where the previous leading entry is at. So this is the first leading entry of the first row. So therefore, for the second leading entry of the second row, it must be to the right of the first leading entry. It cannot be to the left. Okay, but I think this descriptions is much easier for you to memorize it through this kind of example. Basically, we just need to have a like gradually going down stair looking shape. And for the third property, all entries in a column below a leading entry are zeros. So we have seen that, okay, this is a first leading entry, and then everything here is 0, everything here is 0. So all three of the properties are satisfied. So this is an echelon form. And in the matrix next to it, we do not have all 0 rows. And it looks like a stair. And then the leading entries are like with a gradual position. This leading entry is to the right to the first leading entry. 那这个 leading entry 呢，它在第一个出现的 leading entry 的右边的 column， 然后这一个 leading entry 在前面那个 leading entry 出现的右边的 column， 然后这一个 leading entry 在旁边出现的那个 leading entry 右边的 column， 这个也是它都是只会在它前面的 rows 的 leading entry 的右边出现。对， then okay, it satisfies the second property. For the third property, we checked whether the values below leading entries are 0, and it's also satisfied. Okay, so this is echelon form. What about the reduced echelon form? Reduced echelon form. Once the leading entry be ones and there are zeros below and above each leading entry one. So we have more requirement in a reduced echelon form. All the leading entry must be reduced to 1. Those like black box now needs to be reduced to 1. And then also the not just the value below it, but also above it needs to be 0. And now it becomes a reduced echelon form. Okay, here's a definition of the reduced echelon form. If a matrix in echelon form satisfy the following additional conditions， 就是这些 condition 呢是额外的，在除了 echelon form 它必须要满足的3个之外，other than the 3 conditions that needs to be satisfied by the echelon form, we need additional conditions to make it a reduced echelon form or reduced row echelon form, which is the leading entry in each non-zero row is 1, and then each leading entry, leading 1 is the only non-zero entry in each column. So it means that when you have a leading entry, then every element above it and below it must be all zeros. And here's a example of like how do we continue from the previous example. Example 3 continued. This is the previous example where we have identified 3 pivots, but then it is not yet a reduced echelon form. If we want the reduced echelon form, we can perform one operation which is called backward row operations. What we did to reach a echelon form is called forward row operations, a forward row reduction. Now we are going to do it backward row reduction. And the goal is to make these all 1. Okay, this is already 1. And then make this 0. Make these 2 0. Okay. So, okay. So here's the process. You may like take a look at it on your own. We just need to like here it has a row scaling by 1/2 to make the leading entry 1. And then we have continue to have row replacement to make the values above it 0. And row scaled by 1/3. Now this leading entries becomes 1. Okay, the next matrix operations we're going to introduce is called matrix inverse. Matrix inverse. Matrix inverse is defined as follows. This is its definition. If we can find a matrix A inverse and then multiply by A equivalent to identity matrix, and also A right multiplied by A inverse equals to identity matrix, we call this matrix the inverse matrix of matrix A. So the calculation of inverse matrix in a 2x2 matrix is known. Suppose we have A, B, C, D. This is a 2x2 matrices, and then A times D subtracting B times C is not equal to 0. Then A is invertible, and to calculate A inverse, we first exchange the position of A and D, and then both the B and C we add negative signs to it, and then divided by AD minus BC. This is the formula for 2x2 matrix only. And then we can know that this part is the determinant of matrix A. If this part is 0, that means that matrix is not invertible. You are not able to find such a matrix satisfying A inverse times A equals to identity. So that means that's called A is not invertible. So this is a small example, like to calculate the to verify that justify that the C is the inverse of A. Inverse of A is C. So we observe that, okay, how do we obtain such a C? 2 becomes the values right here, and then -7 becomes the values right here. And then this one is multiplied by -1, 5 multiplied by -1, and 3 is obtained via -3 multiplied by -1. That's how we obtain C. And then we can do the calculation whether C is exactly the inverse matrix of A. To do that, we multiply AC, and the result is identity matrix. Identity matrix diagonal entries are ones and then 0 elsewhere. So this is exactly identity matrix. Also, we can multiply, compute the product CA. And then we do the matrix multiplications, find out that this is also an identity matrix. So we have just verified. We have verified C is A inverse. And here it's okay, again a 2x2 matrix. We want to find the inverse of this 2x2 matrix. And then we can first calculate whether the 分母 3 times 6 minus 4 times 5 is 0 or not. And it turns out that it's -2. It's not equal to 0. So it's not invertible. It's invertible. It's not invertible. It is invertible. And so we calculate the A inverse by exchange the position of 6 and 3, and then multiply by -1 for 4 and 5, and then divided by the determinant of it, -2, and then that will give us the inverse matrix. Okay. So we will look at one more theorem. If A is an invertible matrix, n by n matrix, then for each vector B in the Rn space, the equation Ax equals to B has a unique solution. Being A inverse times B. So if A is invertible, it's a good property because now we can match it to uniqueness. Or you know that when we're talking about the equations Ax equals to B, we care about whether it has unique solution or no solution or more than one solution or infinite many solutions. So we have 3 possibilities, 唯一解、无解或者是多重解. And when is the situation that such a equations has unique solution? And you can answer that if A matrix is an invertible matrix. If A matrix is invertible, then we can match it to the solution status. There are unique solution of it. So here's the example. Use the inverse of the matrix A. to solve the system. So we first need to find out what is the system above to convert it into an AX equals to B system. So naturally it becomes like this: 3 times x1, 4 times x2, and 5 times x1, 6 times x2. And then we find the inverse of it to calculate x equals to A inverse B. And then this is a 2 by 2 2 by 2 matrix. So how do we compute the inverse of it? We need to exchange the positions of the values and then multiply by negative 1 for the other two values. And then all of them needs to be divided by negative 2, which is 6 times 3 minus 5 times 4. So that becomes negative 2. And then the result is this one. And we can conclude that A inverse exists and solution 5, negative 3 is unique. All right, so we're going to stop here. And do you have any questions?